Here we are again to debunk the most common misconceptions about the solar system and astronomy. Now we'll tackle 7 of them involving spectacular celestial phenomena like eclipses, fascinating objects like comets, curiosities about giant planets and their moons, and even the history of astronomical discoveries. Follow me closely in our journey. Lunar eclipses are much more frequent than solar eclipses. Many people think that lunar eclipses are much more common than solar eclipses, based on their personal experience of having seen more lunar eclipses than solar ones in their lifetime. In reality, on a global scale, solar eclipses are decidedly more frequent than lunar eclipses. On average, about 2 to 5 solar eclipses, total, partial, and annular combined, occur on Earth every year compared to 2 to 3 lunar eclipses. Over the course of a century, there are roughly 240 solar eclipses versus 150 lunar eclipses. So why do we have the opposite impression? The difference lies in visibility. A lunar eclipse is visible from any point on Earth where the moon is above the horizon, practically half the planet simultaneously, for where a duration can exceed 3 hours in its entirety. Anyone on Earth's night side can observe it without needing to travel anywhere. A total solar eclipse, on the other hand, casts a shadow, umbra, on Earth's surface that can be at most 270 kilometers or 168 miles wide, tracing a narrow path called the path of totality. Only those within this narrow band can observe totality, which lasts just a few minutes. Those in the much wider penumbra zone see only a partial eclipse. Let's look at a practical example. The total solar eclipse of August 21, 2017 was visible in totality only from a strip crossing the United States from coast to coast, about 110 kilometers or 68 miles wide. Millions of people traveled to reach it. In contrast, the total lunar eclipse of January 21, 2019 was visible from the entire American continent, Western Europe, and Western Africa, billions of potential observers. For an observer who stays in the same location their entire life, statistically they'll see many more lunar eclipses, roughly one every 2 to 3 years, than total solar eclipses. To see a total solar eclipse from the same spot on Earth, you have to wait an average of about 375 years. That's why we have the impression that lunar eclipses are more frequent. For us, from our terrestrial vantage point, they really are. But overall, on a planetary scale, nature produces more solar eclipses. Solar eclipses can only be seen from Earth. Since the solar eclipses we know are a unique spectacle due to the incredible coincidence of the apparent sizes of the Sun and Moon as seen from Earth, many think that solar eclipses are an exclusive phenomenon to our planet. But that's not so. Solar eclipses can occur on any planet that has a moon large and close enough to pass in front of the Sun, partially or totally obscuring it. In our solar system, several planets experience solar eclipses. Mars has 2 small moons, Phobos and Deimos. Phobos, the larger one, about 22 kilometers or 14 miles in diameter, orbits so close to Mars that from the Martian surface it appears large enough to create partial eclipses, more properly called transits, because Phobos is too small to completely cover the solar disk. The Opportunity, Spirit, and Curiosity rovers have photographed these transits, which last only a few seconds because Phobos moves very rapidly along its orbit, completing a full circuit in just 7.6 hours. Jupiter offers an even more impressive spectacle. Its 4 Galilean moons, Io, Europa, Ganymede, and Callisto, cast shadows that are perfectly visible on the gas giant's surface. Space probes have photographed these shadows moving across Jupiter's cloud bands. If there were an observer on Jupiter, theoretically, since it has no solid surface, they would see frequent and spectacular solar eclipses. Jupiter's moons are so large that they would create total eclipses far more impressive than Earth's. The same phenomena occurs on Saturn with its numerous moons, on Uranus, and on Neptune. Even some exoplanets discovered around other stars might have moons that produce eclipses, though obviously we can't observe them directly. What makes Earth's eclipses unique isn't the phenomena itself, but the extraordinary geometric coincidence. The Moon has a diameter about 400 times smaller than the Sun, but is also located about 400 times closer to Earth. This makes the two disks appear almost identical in the sky, both about 0.5 degrees of arc, allowing perfect total eclipses where the solar corona becomes visible. This coincidence is temporary. The Moon is moving away from Earth by about 3.8 centimeters or 1.5 inches per year, so in a few 100 million years, total eclipses will no longer be possible from Earth. Hey Curious Squad, before moving on, answering the question, be sure to subscribe to our channel, clicking on the notification bell, and leave us a thumbs up so you don't miss out on our daily videos. All comets have a tail. When we think of a comet, the image that comes to mind is of a bright object with a long tail streaking across the night sky. This iconic representation leads many to believe that comets always have a tail. But no, comets only have a tail when they approach close enough to the Sun. For most of their time, comets are simply frozen nuclei wandering around deep space, cold, dark, and devoid of any visible tail. A comet is essentially a dirty snowball, a nucleus composed of ices, primarily water but also carbon dioxide, methane, and ammonia, mixed with dust and rocky material. The nucleus of Halley's Comet, for example, measures about 15 kilometers or 9 miles in length and is as dark as coal, reflecting only 4% of the light it receives. When a comet approaches the Sun and its surface begins to warm, typically within Jupiter's orbit about 5 AU from the Sun, the ices sublimate. They pass directly from solid to gaseous state without becoming liquid. This gas forms a hazy cloud around the nucleus called a coma, which can reach dimensions of 100,000 kilometers or 62,000 miles in diameter. Solar radiation pressure and the solar wind, a stream of charged particles emitted by the Sun, push gas and dust away from the coma, creating two types of tails. The ion tail, or plasma tail, composed of ionized gas, it appears bluish and is always directed exactly opposite the Sun, regardless of the comet's direction of motion. It can extend for tens of millions of kilometers. The dust tail, composed of heavier solid particles, it appears whitish, yellowish, and forms a curve because dust particles partially retain the comet's orbital momentum while being pushed away from the Sun. Some comets also develop a third component, the anti-tail, which appears to point toward the Sun due to a perspective effect when Earth crosses the comet's orbital plane. As the comet moves away from the Sun again after perihelion, the closest point to the Sun in its orbit, activity diminishes. The tails dissolve and the comet returns to being a simple frozen and inert nucleus. The solar system is crowded with objects. Movies and artistic representations of the solar system often show planets relatively close together. The asteroid belt as a dense region of rocks to be dangerously avoided, and space filled with comets and debris. This creates the impression of a crowded, busy solar system. In reality, the solar system is predominantly empty. The distances and spaces involved are so vast that desert-like would be a more accurate description than crowded. Let's start with the planets. If we represented the solar system to scale with the Sun the size of a basketball, 30 centimeters or 12 inches in diameter, Earth would be a sphere of 2.7 millimeters, smaller than a peppercorn, positioned 32 meters or 105 feet away. Jupiter would be a ping-pong ball, 167 meters or 550 feet from the Sun, and Neptune, the outermost planet, would be almost a kilometer or 0.6 miles away. The spaces between planets are therefore enormous compared to their sizes. The asteroid belt, so feared in science fiction movies, is a perfect example of how empty the solar system is. Located between the orbits of Mars and Jupiter, it contains millions of asteroids, including over 1 million with diameters exceeding 1 kilometer or 0.6 miles. Yet the average distance between these asteroids is about 1 million kilometers or 620,000 miles, more than 2.5 times the Earth-Moon distance. When the Pioneer 10 probe crossed the asteroid belt in 1972, there was concern about possible collisions. In reality, the probe didn't see even a single asteroid during the crossing. Since then, 9 space probes have crossed the asteroid belt without any incident. As Alan Stern, principal investigator of the New Horizons mission, joked, "The chance of hitting an asteroid is so low that if I wanted to get close to one to study it, I'd have to aim precisely." In Star Wars: The Empire Strikes Back, C-3PO warns Han Solo that the possibility of successfully navigating an asteroid field is approximately 1 in 3,720. In reality, the probability of an impact is only 1 in a billion. If the asteroid belt were as crowded as in the movies, mutual collisions would have already reduced everything to dust billions of years ago. Even adding up all the mass of the asteroid belt, which includes Ceres, 940 kilometers or 584 miles in diameter, Vesta, 525 kilometers or 326 miles, and thousands of smaller objects, we'd only get about 4% of the Moon's mass. The distances between comets are even more enormous, and most of them reside in the very distant Oort Cloud, a spherical shell extending up to 100,000 AU from the Sun, nearly 2 light-years, where comets are separated by distances measured in billions of kilometers. The solar system is a vast ocean of emptiness dotted here and there with islands of matter. If an alien were to cross it blindly, they'd need extraordinary luck to run into even a single planet. Gravitational force on a planet depends only on its mass. Many think that the more massive a planet is, the greater the gravity on its surface will be. Following this logic, Jupiter, the solar system's most massive planet, should have the most intense surface gravity. In this case, too, things aren't exactly like that. A planet's surface gravity actually depends on both its mass and its radius. More precisely, surface gravitational acceleration is given by the formula G equals gm divided by r squared, where g is the universal gravitational constant, m is the planet's mass, and r is its radius. This means that a planet can be very massive, but if it's also very large radius, its surface gravity can be surprisingly low. The most striking case is Saturn itself. Despite having a mass 95 times greater than Earth's, its surface gravity, measured at the level of the upper clouds, since it's a gas giant, is only 1.065 g, just 6.5 more intense than Earth's. How is this possible? Saturn has an enormous radius, about 58,000 kilometers or 36,000 miles, almost 9 times Earth's. The mass is distributed over such a vast volume that the surface, or what approximates it, is very distant from the center of mass. Saturn is in fact the least dense planet in the solar system, with an average density of only 0.687 grams per cubic centimeter, less than water. If there were an ocean large enough, Saturn would float, though this is a purely theoretical image. Jupiter, with a mass 318 times Earth's, has a surface gravity of 2.528 g, 2.5 times Earth's. Significant, certainly, but much less than you might expect from its mass. Jupiter, too, is a giant with a radius of about 70,000 kilometers, or 43,500 miles, roughly 11 times Earth's. On the opposite end, consider the Moon. It has a mass of about 181 of Earth's and a surface gravity of 0.166 g, about 1/6 of Earth's. If we compressed it to reduce its radius to 1/3 of its current size, about 580 kilometers or 360 miles, while maintaining the same mass, its surface gravity would increase 9-fold, becoming greater than Earth's. An extreme example from the cosmos: neutron stars. They have masses similar to or greater than the Sun's, which is 333,000 times more massive than Earth, but radii of just 10 to 20 kilometers or 6 to 12 miles. The resulting surface gravity is billions of times more intense than Earth's, so strong that the escape velocity is about 1/3 the speed of light. Venus has a mass slightly less than Earth's, 81.5% of Earth's mass, but having a similar radius, has a surface gravity almost identical to ours, 0.904 g. This principle is fundamental for understanding the habitability of extrasolar planets. A rocky planet might have several times Earth's mass, a super-Earth, but if it also has a proportionally larger radius, its surface gravity could remain tolerable for life forms similar to ours. Pluto, like Neptune, was discovered through mathematics. The story of how Neptune was discovered is famous. In 1846, astronomers Urbain Le Verrier and John Couch Adams mathematically predicted the position of an unknown planet based on gravitational perturbations observed in Uranus's orbit. When the telescope was pointed in the calculated direction, Neptune was found almost exactly where predicted. Many believe that Pluto was also discovered in the same way, by calculating where it had to be to explain additional anomalies in the orbits of Uranus and Neptune. Wrong. Pluto was discovered through a lucky coincidence, not through accurate mathematical calculations. The story is a fascinating example of how science can progress even when the premises are wrong. After Neptune's discovery, astronomers noticed that small discrepancies persisted in the orbits of Uranus and Neptune that couldn't be completely explained by the known planets. American astronomer Percival Lowell was particularly convinced of the existence of a ninth planet, which he called Planet X, and spent years together with William Pickering calculating its theoretical position based on these supposed perturbations. Lowell died in 1916 without having found his planet. In 1929, Lowell Observatory hired a young astronomer, Clyde Tombaugh, to continue the systematic search for Planet X. Tombaugh worked tirelessly, photographing regions of the sky and comparing photographic plates taken days apart to identify objects moving against the background of fixed stars. On February 18, 1930, after months of meticulous work, Tombaugh identified a small point of light that had shifted in images taken on January 23rd and 29th. It was Pluto, and the new arrival had been discovered less than 6 degrees from the theoretical position calculated. But here's the problem. Pluto is too small and light to cause the perturbations that Lowell had calculated. With a diameter of only 2,376 kilometers, or 1,476 miles, smaller than the Moon, and a mass of just 0.0022 Earth masses, less than 1/5 the Moon's mass, Pluto is entirely insufficient to significantly influence the orbits of Uranus and Neptune. The mass that Lowell had estimated for his Planet X was much greater, similar to Earth's. The discovery of Pluto in the general region predicted by Lowell's calculations was therefore pure coincidence. In the 1990s, when the Voyager 2 probe flew by Neptune and allowed precise measurements of its mass, astronomers recalculated the orbits of Uranus and Neptune. The discrepancies disappeared completely. The perturbations were due to imprecise estimates of Neptune's mass, not the influence of an unknown planet. In other words, Lowell was looking for a planet that didn't exist, based on erroneous data. Tombaugh found Pluto, not where calculations truly predicted it, but in an area he was systematically scanning anyway. He was lucky. Pluto is now classified as a dwarf planet and is recognized as the prototype of trans-Neptunian objects in the Kuiper Belt, a region populated by thousands of icy bodies beyond Neptune's orbit. Its discovery was important, but the romantic story of mathematical prediction is, unfortunately, a myth. Jupiter, the largest and most massive planet, hosts the greatest number of satellites. Jupiter is the solar system's giant. It has a mass 2.5 times greater than all other planets combined, possesses the most powerful magnetic field, the Great Red Spot, a storm that lasted at least 350 years, and the 4 spectacular Galilean moons, Io, Europa, Ganymede, and Callisto, discovered by Galileo Galilei in 1610. With all this grandeur, it seems logical that Jupiter would also hold the record for the greatest number of natural satellites orbiting it. Wrong again. Because in reality, as of March 11, 2025, there are 274 moons of Saturn with confirmed orbits, the most of any planet in the solar system, while Jupiter, on the same date, counts only 97. This relatively recent discovery is due to advances in observation techniques and systematic telescopic surveys that in the last 20 years have revealed dozens of previously unknown small moons around the gas giants. Most of these new moons are tiny objects, some with diameters of just 1 to 2 kilometers, or 0.6 to 1.2 miles, often fragments of larger bodies destroyed by collisions or captured by the planet's powerful gravity. Many of these irregular moons orbit at great distances from the planet, have retrograde orbits, moving in the opposite direction to Saturn's rotation, or highly inclined ones, suggesting they were objects captured from the Kuiper Belt or cometary cloud, rather than having formed together with Saturn from the original protoplanetary disk. Why does Saturn have more moons than Jupiter? There's no definitive answer, but some hypotheses include Saturn's more distant position from the Sun might have facilitated capturing objects from the Kuiper Belt. Saturn's ring and moon system structure might be more favorable for minor satellite formation, and Saturn's collisional history might have created more fragments that became independent moons. It should be noted that the exact count of moons continues to change as new tiny moons are discovered, and that the criteria for defining what constitutes a moon versus a temporary fragment in the rings or orbiting debris is still subject to astronomical debate. But at the present moment, Saturn is the clear winner. Far behind are Uranus with 29 confirmed moons and Neptune with 16. Okay guys, so what do you think? Which of these debunkings surprised you the most? And which ones do you still have serious doubts about? Let us know in the comments. And if you want to learn more, check out the complete series we've dedicated to this argument.